My dear friends, welcome back to Bee Spice. In this session, we'll talk about alarm philosophy in line with EEMUA 191 Appendix 3. So, what is EEMUA? Engineering Equipment and Material Users Association, okay, which is the best practice for alarm management. So, hope you had watched my previous session on alarm management, wherein we covered, uh, the alarm management in a more general way. Of course, most of the things we have already covered, but in this video, we are going to, talk in line, specifically in line with the EEMUA 191 guidelines. Okay, friends? Yeah. So if you have not watched the previous video, you can watch actually. Okay. And this video is exclusively for the members. Okay, friends? Right. So what is the agenda? Okay, we'll directly jump on to the alarm priority index. Okay, plan operation consequence POC. Then we also talk about time to consequence. We call it as TTC. Then alarm priority level with the typical examples, alarm types, process alarm types, EEMUA 191 third edition 2.4.1. Then levels of safety, alarm states, and finally we'll touch upon a bit on the suppression, alarm suppression techniques. Okay, friends. So these are the agenda. Let's move on with the details. Okay, alarm priority index. See, alarm priority index is nothing but an index number. What is that index? Anything between 1 to 25. Okay, so that is the alarm priority index. Okay, this is for what? For the determination of the desired operator response. We need to determine the operator response in line with this priority index. Okay, we need to assign a priority index for each operator response. I'll be covering that one by one, don't worry. Okay, so this index actually assists the operator in decision. Okay, which alarm is more important, as the operator might be overcharged to judge correctly due to the possible, complexity of the alarm, its causes and actions, and the short time available. So basically, this priority index will help the operator. Okay, so that is a point actually. Okay, but the challenge here is it may require an assessment team to work through each alarm to provide a quantitative estimate. You got it, friends? There are a lot of alarms, so you need a team to work through each alarm to provide a quantitative estimate. So to get, to mitigate this, an alternative heuristic method is used, which is more of a qualitative approach based upon severity. I hope you watched the previous one, right? Yes, the alarm management wherein we talked about severity, right? Here also we are going to focus, but specific to this EEMUA. So the alternative method is to, more of a qualitative approach based upon severity uh, uh, in line with method 1 of Appendix 3. Standard Alarm System Guide to Design Management and Procurement, publication 191, third edition. Okay, so that is what we are going to follow, and we are going to see what is there. So most of the projects actually calls for this requirement, friends. EU MUA 191. Okay. Some cases, just I want to add on a bit. Some cases, sorry, just hold on. Some cases actually, some projects, they also refer to ISA section actually. So what is that ISA? Just hold on. Yeah, ISA 18.2. Okay. So that is also, some projects call for it. But most of the projects, we work with this EEMUA 191. Okay, friends? So now good to go. Right. So then here, similar to what we discussed earlier in the previous, the video alarm management, wherein we talked about the, severity and the time response, right? The same thing, we are going to have a new terminology here. plant operation consequence, POC. This is the severity. So basically what is POC? It is the potential consequence of the alarm if no action is taken. Okay, just remember this word POC. We are going to discuss the whole session with this POC and TTC. Okay. So what is TTC? TTC is the time to consequence. Basically, estimated time required for an operator to take corrective action. That is basically the operator response time. Okay, friends? I hope this slide is clear. Right. Now we go to the POC. Okay. Okay, friends. So POC, what we discussed earlier. So it is basically, what is that? Potential consequence of the alarm if no action is taken, right? So I've classified this so as a five categories. Friends, if you look at it, POC 1, 2, 3. Okay, 1, 2, 3. POC here 1, 2, 3. This actually covers mainly financial impact. Okay, POC 4 refers to the environmental impact, and POC 5 is related to the process design limits. Okay, just remember this, friends. This is very, very important. Okay, now we'll go one by one. POC index 5. This is related to over pressure, over temperature, relates to process design limits with the risk of loss of containment and major destruction to the processor. Okay, equipment. You got it? Okay. So, number 4. This is environment impact, right? Yes. Chemical compounds released to atmosphere, liquid released to environment, significant violation of emission limits. Just remember this, friends. POC 4. Then POC 3. Mechanical failure, severe unit upset, loss of pump or compressor, loss of control relates to possible excursions from the normal operating state, possibly leading to opening of a mechanical safety relief device or a trip of a major equipment like boiler, turbine, etc. Okay, so this is very, very important. Just remember this. POC 3. Then, of course, we have POC 2, but it is, risk for substantial reduction of plant performance, in terms of electricity or output, all these. Okay. Then POC 1 is nothing, it's a minor reduction. Okay, just remember this, friends. Okay. Now, we go to time to consequence, TTC. Okay. So in TTC also, we have five categories. Here, one point I want to touch upon. See, a corrective action which must be executed by the field operator. The field guy, field operator is weighed at a higher level compared to the DCS operator. Why? Because field operator will have to travel to the point at which he has to take a corrective action, right? Yes, that location might be far away from the actual position, right? So that is why the corrective action which must be executed by the field operator is weighed at a higher level compared to the DCS. So that is why TTC index 5. Field operator responds within less than 5 minutes. Got it, friends? Yes. So DCS operator responds with less than 5 minutes. 4. And field operator responds with less than 30 minutes but more than 5 minutes. So 5 to 30 minutes. TTC 3. Okay. Then DCS operator responds within less than 30 minutes but more than 5 minutes. So 5 to 30 minutes, DCS operator 2. Then operator response expected but not time critical. We have the luxury of more than 30 minutes. That is TTC 1. So now you remember both, friends, this POC and TTC. Okay. I hope this is very clear. Okay. Let's move on. This is the climax. Okay. So now, similar to what I did earlier in the previous video, the severity, and also the time response. So similarly, in line with EEMUA, we actually matrix this, okay, the index, how with the plant operation consequence POC, that like here 1, 2, 3, 4, 5, right? Yes. Then time to consequent TTC 1, 2, 3, 4, 5, right? Yes. So this is the matrix. So I'm going to explain with a typical example. In fact, one of our friend, actually the subscriber actually asked to explain actually. Of course, not for this, but he wants some process related explanation. So that is why I'm going to explain now with an example. Okay. Okay, friends. So if you can see here in the table, friend, consider a case in my project, low boiler drum level. Okay, just listen carefully. Low boiler drum level. I'm going to talk more. I'm not going to put anything in the wording. I'm going to talk more on this. Okay. So boiler, low boiler drum level warning. Okay. So this refers to a condition that may exceed process design limit, right? With risk of loss of containment, right? Yes, it is a hazard. But the hazard is safeguarded by means of a safety instrumented function, right? So ultimately, the plant operation consequence is not a loss of containment, but severe unit upset due to the resulting boiler trip. So if you remember the previous POC table, so the POC is here it is 3. Remember, friends, for the plant upset, right? Yes, that is POC 3. Okay. You want me to go back? Okay, I'll go back for you. You can see here, this is the one, trip of a major equipment, right? This is POC 3. Okay, then come back here again. Yeah. So that is the POC 3. Then here, if you talk about the TTC, a field operator response is within 5 minutes is expected, right? Because, this is important, right? Yes. So field operator, okay, you can see here, field operator response less than 5 minutes is required. So that means TTC 5. Okay. So here POC 3 and TTC 5. So now we fall in this category. This is 15. Okay, which means critical, right? All these red are critical actually. Okay. Okay, friends, you got it? Yes. So that is how we need to calculate. We have to come out with the priority index. Okay, good to go. Now, I will also explain one more. Now we are previously we talked about low boiler drum level, right? Now I'm going to talk about low drum level. Okay, so it informs the operator that the above described safety instrumented function has intervened to avoid a loss of containment scenario. Okay, but the consequence remained the same, meaning severe upset due to the boiler trip. So again here the POC is 3. Okay, but now operator response is now not time critical because the fail-safe controller has already taken the decision in the operator place to trip the boiler to bring it to the plant to the safe state, right? So here we need to actually what do you call that? Expected operator response is to investigate the cause of the trip and to give the necessary information to the maintenance team on what has to be repaired to allow for resuming the operation. So the time the operator needs to investigate the cause of the boiler trip is not relevant anymore in an attempt to prevent this boiler trip. Of course, the operator is not supposed to waste time in investigating the cause, but he can afford more than 30 minutes, right? As his response time is generally negligible, right, friends? So in that case, it is TTC 1. So you see POC 3 and TTC 1. So now we are falling in this category, right? So this is low. You got it? Yes. Very good. Good to go. Then also one more example I want to give you. Low level warning in ammonia storage tank. What will happen? That can lead to a significant violation of emission limits, right? Yes. So in that case, emission limit, environment POC 4, right? Yes. So here operator response within 30 minutes is expected, right, friends? So if it is within 30 minutes, that means it comes under TTC 2 actually. Okay. So you see POC 4, okay, and TTC 2. That means what is this? 8. So it is high. Okay. So if it is red means it is critical and this means high. Okay. Priority is high. Okay. Got it, friends? Okay. Good to go. So this is how we need to, come out with a alarm priority index. Okay. Now, another one, so typical case, a primary air fan actually. So it trips actually, it trips. So, but here there is no plant upset actually. Yeah, it trips actually. but meaning less combustion are available, resulting in a less waste throughput. So it can cause a substantial reduction of plant performance without causing a boiler trip. So that means no severe unit upset, right? So in that case, we can go for POC2, right, friends? So here also operator response expected, but not time critical. So that means TTC1. So here POC2, TTC1 here, it falls under 2, right? So priority is low. That's it, friends. This is how we need to come out with the alarm priority index. I hope this is very clear. Okay, good to go. Anything you can write to me. Okay, be spies for you at gmail.com. Okay, so now we have learned the alarm priority index, how to read all these. Okay, now we'll see them how to assign the priority level. Okay, there is some formula actually. Okay, not formula, some criteria. Okay, see priority level. If you see, if you referred our previous video, we only talked about high, medium, low, right? But here we also added critical. So critical, high, medium, low. Okay, this is the priority level. And if we talk about the priority index, 25 to 15, this is the priority index. The previously we talked, right? The priority index, right? So 25 to 15. So for that, what is the alarm target? 20 per major process equipment. Okay, 20 alarms per major process equipment. That is the target. So that comes under 25 to 15. That is the index here, right? So in this case, 25 to 15 means here. Okay. So in this, if it comes in this region, then it is critical, right? Red one critical. So for that, we need to target 20 alarms per process equipment. Okay. Then for high, you see 14 to 18, 14 to 8 and 5% of the total alarm. Okay. So if you have, 100 alarms, so 5% of the total, that is 5 numbers. So that will be classified as a high and the alarm priority index is 14. I hope you are following, friends. See, alarm target 20 per major process equipment, 20 alarms per major process equipment. So that is actually classified as a critical, okay, and the alarm priority index 25 to 15. So 5% of the total we classify as a high, okay, alarm priority index 14 to 8. Then 15% of the total alarm, okay, class with alarm priority classified as a medium and alarm priority index 6 to 4. Then 80% of the total alarm 3 to 1 alarm priority index and it is considered as a category low. So if you look at this, the point is you cannot have more critical alarms, friends. That is the point. Okay. So only 20 per major equipment we need to classify as a critical. Then 5% high, medium 15% and low 80%. From this you can able to identify, right? Yeah. So I hope this is also clear. Okay. Yes, very good. It's all in line with the EEMUA, friends. Okay. So I think should be okay. And what else you want to have it here? I think should be okay. Then we go to the alarm types. This is also very important. If you remember the previous video, what we talked about the alarm different types, right? So we focus only on the process alarm type. We talked about the deviation, rate of change of alarm, pattern alarm, absolute alarm, dynamic alarm, re-alarming, all these, right? Similarly, as per EEMUA 191 third edition 2.4.1, four types of alarms are used. One is the process alarm, equipment alarm, instrumentation alarm, and control system alarm. Okay. Then we go back to the process alarm. In fact, I covered extensively basically what we talked deviation alarm, right? So deviation means difference of measurement from set point and rate of change of alarm means used to detect the beginning of a exothermic reaction and pattern alarm is two or more plant condition can be tracked and also the absolute alarm that is the normal that low, high, low, high alarm all these. Then dynamic alarm is these triggers can be automatically change alarm set point based on the priorities, right? So the re-alarming. So alarm could be alarmed again if the problem has not been corrected from the alarm response. This is about the alarm, process alarm, which we discussed earlier. So coming back to this EEMUA, okay. So how to what do you call, how to classify the how to come out with the priority, the priority matrix, right? Yes. For example, you consider a case of the deviation alarm. Okay, just for example, friend, in this process alarm, I'm talking about the deviation alarm. Deviation alarm is in between redundant analog signals, right? Correct, friends, right? So in most cases, an intervention from the maintenance team will be needed for this, right? So in this case, we can consider as a POC3 because possible loss of control leading to a process excursions from the normal operating state, right, friends? Right? So that is why, POC is equal to 3 in this case, process alarm, the deviation alarm. Okay. But here, one point I want to highlight also, in case the instrument is part of the safety instrument function, okay, protecting against the loss of containment scenario due to overpressure or over temperature, and the deviation of the instrument could lead to a dangerous failure of safety instrumentate function, right? So in that case, the POC has to be increased to 5. You got it, friends? So normally for a process deviation alarm, POC is 3 because possible loss of control leading to process excursions, right, friends? But in case of safety instrumented function, protecting against the loss of containment scenario due to overpressure or over temperature, the deviation of the instrument could lead to a dangerous failure of its safety instrumented function. In that case, it will go to POC 5, right, friends? Okay. Then coming back to this TTC, here the operator response is expected within 30 minutes, right? So in that case, we can go for a TTC2. Okay, that's it. So that is how we need to, come out with the matrix, okay, priority, right, friends? Okay, good to go. So now I have POC3 and I have TTC2. Okay. Okay. Maybe I go back here again to talk about the matrix. See, I have a POC3. Okay. I have a TTC2. Now, what is this 6? So, this is the priority index for this deviation alarm. You got it, friends? Yes. Good to go. So, likewise, I want to talk about the equipment alarm also. Okay. Maybe I'll go back again. So we talked about process alarm. Now I'm going to talk about equipment alarm. Just listen. Equipment alarms are nothing but a discrepancy alarm on motors, valves, etc. Right, friends? See, electrical motors can generate motor alarms, right? Yes. Like for example, frequency drive error or MCC drive not available. Also, discordance alarms on motors. You know what is discordance alarm? In case a start command is not followed by running feedback, then when the running feedback does not disappear, when the start command is withdrawn, this is the discordance alarm. You are following, friends? In case a start command is not followed by a running feedback, and when running feedback does not disappear when a start command is withdrawn, so this is the discordance alarm. Okay. So yeah, so likewise, this is classified under equipment alarm. Okay. Now, if we talk about this POC here, there is a risk of substantial reduction of plant performance here. Okay. So that means POC2 actually. So POC2. Okay. So this is the equipment alarm. Okay. Maybe I'll go back here so that you can understand this POC2 actually. Yeah. You see, risk for substantial reduction of plant performance because of this. Okay. So my POC is 2, right? Yes. So my POC is 2. Just remember this. Then here operator response is expected, but not time critical, right? So it can generally be not expected from the DCS or field operator. They should immediately solve a motor or valve failure. In most of the cases, they have to engage a maintenance team, right, friends? Yeah. In general, the DCS operator forget and ignore the alarm is relatively low. As falling motors and valves will usually hinder his ability to continue the operation in a proper manner, right? So what he will do, he will just inform the maintenance team. So mostly not time critical. So if not most time critical, that means it is 1. So POC 2 and this is 1, right? So what is this? Priority index is 2. Got it, friends? Yeah, very good. So that is how we need to come out, friends. Okay, so now we are done with the process, equipment, and yeah. So now we go to the instrumentation alarm. Okay, instrumentation alarm, our domain. Okay, so instrumentation alarm deal about analog transmitter, right? Like out of range. Yeah. So basically, how what will happen? Short circuit resulting in overcurrent or broken wire, right? Resulting in no current, right? Yes. So yes. So now what we can do? We can have a POC of 3 because possible loss of control leading to process excursions, right? Yes, POC 3. And here again that operator response expected but not time critical, right? Because this year's operator informs the maintenance team, right? Yes. So TTC 1. Okay. I go back again here. See POC 3, right? POC 3 and TTC 1. Now what is this 3, right? So again, this is a what? Low, right, friends? So that is how we need to categorize. Okay, got it, friends? Now we are done with process. We are done with the instrumentation equipment. Now control system alarm. See, what is this control system alarm, friends? Generally, these are registered in a separate alarm list, right? Or they will be separately identified in a way that operator can filter out from the alarm list. See, what is this actually? Loss of field bus communication with subsystem, right? Package unit. This is considered as a control system alarm. Okay. So here again, a substantial reduction of plant performance. So in this case, again, I'll go back. It is 2, right? Yes, POC 2. Okay. Yeah. What else? Yeah, of course, this whatever the communication laws, the designer of control system has a high redundancy, right? In a way, most of the control system alarms will not have an immediate consequence, right? Yeah. So POC 2 only, yes. Then what is this TTC? TTC, control system alarms are not considered as the responsibility of operator, right? Because it's a communication. Their interpretation requires, dedicated expertise, right? So the operators simply he need to inform the automation team to undertake the necessary action. So POC 2 and TTC 1. So that means again priority index is 2. You got it, friends? I hope now this is clear, right? So this is how we need to come out with the priority level so that it is easy, right? Yeah, you got it right. Okay, good to go, friends. So now we are done with alarm types. Now we are into levels of safety. There are 5 levels of safety for plant operating, friends. Okay. So one is the lowest level. Okay. Second is a pre-alarming or warning level. 3 is the alarm level. Fourth, alarm level plus DCS interlock. 5 is the alarm level plus safety interlock. Okay, these are the 5 levels of safety. So now let us see what is the lowest level. Lowest level is normal operation of the plant by means of an automatic condition, right? Okay. Then what is the pre-alarm or warning level? The operator is informed that something is operating outside the normal process boundary. Okay. So if no action is taken, the situation will lead to an alarm and probably interlocking of components. Okay, friends? Right. Then alarm level. The operator is informed that something is going wrong, right? And quick action might be required to prevent interlocking of components. Right, friends? Right. Then yes, alarm level plus DCS interlock. The operator is informed that something is going wrong and the action has been taken by the normal control system, that is the DCS interlock. Here, alarm level plus safety interlock. The operator is informed that something is going wrong, but here the action is taken by SIS, safety instrumented function. So this is how we need to classify 5 levels of safety. Okay, friends? So safe level of safety is different from alarm priority index and no direct correlation between these two properties. Okay, friends? Okay, don't get confused. Just I want to explain this levels of safety. Okay, right. So what else? Yeah, yeah. Now we'll go to the Alarm state. This is bit of explanation is needed. Yes. For example, friends, we should know actually what I'm going to explain here. See, it must be clear to the user which state an alarm is in. You got it? User must be very clear and he should know which state an alarm is in, right? Okay. So for example, in this diagram, we have, states, right? State means this is a bubble, okay? And transition condition, that means arrow, okay? Just listen carefully, friends, okay? When there is a no alarm condition, alarm is activated, yeah, here, right? Yeah. When there is a no alarm condition, okay, alarm is, yeah, sorry, alarm is deactivated. The process will be in a normal state, right? This is the A, normal process, okay, alarm, okay, all okay. If the alarm condition becomes true, alarm is activated, right, friends? Okay. So the process will come in alarm where the alarm is acknowledged here, right? B. So when the operator acknowledges the alarm, then the alarm will be acknowledged. Yeah, sorry. Here unacknowledged, right? Yes, yes. So the process will come in where the alarm is unacknowledged, right? Here, right? Okay. When the operator acknowledges the alarm, then the alarm will be acknowledged here. C, right? Yeah, operator acknowledges the alarm and it is in the C state. Okay, got it. So if the alarm condition clears, operator must reset the alarm, after which the alarm state will automatically go back to normal. Isn't it, friends? Okay, so alarm is again deactivated, right? If an alarm condition go back to normal before the operator acknowledge the alarm, it will remain in the alarm state, meaning alarm remains activated until the operator reset the alarm. So here, this guy, returns to normal, alarm remains actually. You got it, friends? So if a condition goes back to the normal, if an alarm condition goes back to normal before the operator acknowledge alarm, then it will remain in the alarm state, meaning the alarm remains activated until the operator reset the alarm. Okay, so now in D. So the reset of an unacknowledged alarm automatically acknowledges the alarm as well as the cause of alarm has been solved. Okay, right. So that is what, return to normal, operator reset, automatically acknowledges. Okay, so this is how, we need to come out with this, understand the alarm state. So that is why I explained here. I hope this is clear. I hope this is clear. Anything, yeah, anything you can always write to me, friends. Okay. So basically, I explained this. We should know what is the alarm state. Which state the particular alarm is there. That's why it's all actually add-on, friends. The priority level index all done. And the last slide, whatever we have covered, levels of safety, and this all add-on. Okay. Now, the final one, friends. You may be, you might have heard that, a lot of companies, the system vendors, they have been, talking about, alarm rationalization, all these, right? Yeah. So I'm going to see some of the few, thing. Of course, in future, if we have our own school and, we have our own DCS system, then we can, add on this alarm rationalization software and we can work out. That's a long-term plan. But now for this case, you get to know this techniques. See, basically, alarm delay times that will reduce the chattering alarm caused by the discrete signals or by process fluctuation on analog measurements. Got it, friends? See, we need to delay the alarm. So that will reduce the chattering alarms caused by the discrete on-off signal or by process fluctuation on analog measurement. So this is the delay. One is one of the technique. Okay. Then we should have a procedure to acknowledge and reset alarm will reduce the repeating alarms. Like what we discussed, right? We should have a procedure to acknowledge and reset which will reduce the repeating alarms. That is the second item. Then third item, redundancy alarms are avoided unless required for the diagnostic purpose. For example, to discover a drifting transmitter which is not following the other in the 2 out of 3 architecture. Okay. So, like you have a 2 out of 3, and the redundancy alarm we don't have to, we just avoid. We just avoid. So that is one of the aspect we can consider. And alarm, yeah, grouping of alarm. Okay, uh, grouping of alarm. So grouping of alarm for subsystem connected via field buzzer. In case of a connection fault, only loss of communication will generate an alarm, but the missing signal will not generate the individual alarm on their own. You got it, friends? So we should group the alarm for the subsystem. Okay. So thereby, in case of a connection fault, only the loss of communication will generate an alarm, but the missing signal will not generate alarms on their own. Then static suppression actually. See, what is the static suppression? Basically, when equipment is out of service, for example, waiting for the next overhaul, the equipment alarms won't be active when the operator uses the object lock function on the supervision screen, right? So the object lock function has the same functionality as a mechanical padlock on an MCC drive or a mechanical padlock on a remote control valve. But now on the supervision screen, but now on the supervision screen of the DCS. So basically what happened, the change from locked to unlock condition, okay, and from, unlock to lock condition can be done under the supervisor password level, okay. So in lock condition, equipment alarm will be suppressed. So that is the point, friends, okay. So an equipment is out of service, okay. So we can do this lock condition, and in that condition, equipment alarms will be suppressed. So that is the point. Then again, another point. State-based alarming is only allowed if the process state can be determined automatically. What is that? Process state can be determined automatically. Some of the example. See, for example, we are disabling the low flow alarm when pump is not running, like logical suppression, right? We are disabling the low flow alarm when pump is not running. And another case, real process value on analog transmitter are ignored when they are in the simulation mode, right? Yes. So, yeah, these are the things we can actually go for it. Okay, state-based alarming. Okay, right. Then another one is, yeah, I think that's all. I think, yeah, yeah, yes. One moment. Yeah, I think that's all, friends. Good to go. So I hope you had a very, good insights on various aspects of this alarm philosophy in line with EEMUA 191. Okay. So as a recap, what we talked about priority index. We talked about the plant operation consequence, POC, that is the severity, and time to consequence, that is a time response. Then alarm priority level with a lot of example. Then alarm types also we discussed. Then we talked about the levels of safety and alarm states and the alarm suppression techniques. Hope you will like this video. If you like this video, you can show your support by pressing the thumbs up button. Okay. And yeah, if possible, you can subscribe and become a member for more, videos like this, friends. See you soon. In fact, I'm planning to, talk about the Yokogawa DCS in detail. First, I want to talk about, the funda. Then I talk about the engineering, the real engineering, how we are going to do. All those I'm going to take as a master series, and keep supporting, keep watching. Till then, this is Ram Bala signing off. Bye bye, friends. Take care.